Good afternoon, everyone. On behalf of Department of Electronics Engineering and RAIT, I welcome you all for today's session 2 of our AICTE approved ATAL FDP on robotics. During this COVID-19 pandemic, a recent report in Financial Times has highlighted the boost received for robotics and automation across the world. Asimov proposed three laws of robotics. So, Law 0 says a robot may not injure humanity or through inaction allow humanity to come to harm. Research and development is being done on a large scale in developing prototypes using robot operating system ROS. The integration of ROS has increased and supported the ground use of robots around the globe and is the key driver for the inevitable robot field future. It is my proud pleasure to welcome one of our own alumnus, Mr. Ajit Mutalik, our esteemed speaker of today's session. Mr. Ajit Mutalik is a bachelor's in electronics and telecommunication from RAIT. He is currently working as project associate at the Indian Institute of Technology, Kanpur, under the guidance of Dr. Mangal Kothari. His current research focuses on developing an indigenous autopilot stack for autonomous aerial vehicles using CDAC's Vega microprocessor, which is based on RISC-V architecture. During his bachelor's, he has developed a mobile robot and planet tilt system for mapping hazardous underground coal mines. He, along with his teammates, has also won multiple project competitions such as Smart India Hackathon Hardware Edition 2019, eYantra Ideas Competition 2018, and Srijan 2018 during his period as a student of RAIT. So today we have Mr. Ajit Mutalik with us. The session will introduce us ROS architecture. It will also focus on what is 3D robot modeling in ROS for gazebo simulator, as well as it will demonstrate how to add sensors and simulate the robot using ROS and gazebo. Now I request you to kindly start your session. Over to you, Mr. Ajit. Thank you.
Hello everyone, can you hear me? Um, Hello, my
Yes,
name is
yes,
Ajit Mutalik.
yes, we can hear you.
Um, okay, I've shared my screen. Give me a second. Hello everyone, my name is Ajit Mutalik. I'm currently working as a project associate at Aerospace Engineering. My principal investigator is Dr. Mangal Kothari, and my field is mostly on embedded systems and computer vision for localization and mapping. So today I'm going to take a workshop on gazebo and a basic hands-on approach on gazebo and robot operating system. So here we go. So in the morning, Lentil Joseph sir gave us a quite good introduction about what is ROS, but still I'll give a little bit introduction about ROS and how it is going on. So ROS, Robot Operating System, is a meta operating system, something which is not completely an operating system, but an overall framework for integrating all the sensors, all the programs together. So the robot operating system is completely open source and it runs on Linux. Recently, Windows support is also rolled out, but it is a bit on base beta development, so it is not suggested to be used. But Linux, it is well supported and well developed. Then there are things which ROS helps us to do a lot, such as hardware abstraction, low-level device abstraction, message processing, and package management. So what do you mean by hardware abstraction? So there are sensors which are used in your robots, like GPS sensors, wheel odometry sensors. Then there are IMU sensors. So all these sensors, when you're working on embedded systems, you require those libraries to interface with your code or with your system. So for this, ROS is an excellent architecture because it provides you with the ability to create nodes, It gives you a message structure to pass your messages of the incoming sensor data to other nodes which are present in the system. It also provides sensor libraries for interfacing. So if you have a GPS sensor, which is an I2C based sensor, which communicates on I2C bus, so you have those libraries as well to interface with the device and with the main computer. Then the most important part of robot operating system is the message parsing architecture between processes. So when you say when your multiple processes working together, they need to talk with each other, right? For this, ROS is an excellent architecture which provides this subscribe message architectures, and which is really important when you come to in field of robotics, because there are so many things going on with sensors, with planning, with vision, and this helps a lot. Then package management. So there are a lot of packages which you use in your robotics robot which you use. So let's say if you're using a if you're using a mapping software, say G mapping, which is a SLAM algorithm, open source SLAM algorithm implemented into a package, you are free to download those packages and use in your own system. This is very helpful when it comes to quick prototyping of the system. And this is really well integrated in complete ROS architecture. So right now, ROS is getting scaled up to many different CPUs as well. It is also supporting ARM architecture. It is supporting Intel architecture, and it is going into more and more embedded systems. So there is also micro ROS, which helps you. Uh, Basically, all the ROS has been tuned down for getting into on embedded systems. So why ROS? Like, what is the main idea behind the ROS? Is the thing is when you're in robotics, you do things again and again and again. So to stop this reinventing of the wheel, uh, people at Stanford came up with ROS, which was taken over by Willow Garage afterwards, and this has been an quite a de facto operate framework which is used in robots and very high level robots and even in small robots, which is helpful. So the philosophy of the ROS is peer-to-peer communication between nodes, which is basically sending the messages, sending the data between the nodes for communication to take the decisions upon the incoming data from the sensors. Then there is distribution of the nodes on the different computers. So thing is, ROS works on well on network. It communicates via TCP/IP. So you can run ROS on multiple computers at a single time, and these multiple computers can communicate with each other if they are on a single network or if they are on internet as well. So if you properly configure it, you can communicate over the internet. Next thing about ROS is it's multilingual. So there are many languages that have been supported by the ROS, mainly C++, Python, Java, and there are many more. Just to mention few. Then the best thing about ROS is it is completely open source. So any person can pick it up. Any person can use it in their robot without any licensing or any other things. So that is the basic philosophy of the ROS. Then coming to ROS, there are few core components of the ROS which we need to know. So first one is ROS master. So this is the main channel of communication between the nodes. And every time the nodes get start up, this every node has to get registered into ROS master. So to start the ROS master, you can just use the ROS core, which is a command to start the ROS core in the terminal. Then comes ROS nodes. So ROS nodes are basically an executable programs which you develop in your systems. So let's say if you're working on computer vision and you need to do some kind of detection of an object or segmentation of the roads or incoming data, then you will just write a node regarding to the computer vision, and you can use the overall ROS framework around it just to use the your algorithm into actual robot, and overall it will help you a lot. Then these nodes are individually compiled and executed. And to run a specific node, you use this command. So say ROS run package name and the node name. So since there are multiple packages, you have to define which package you are going to use and the nodes which are present into that package, specific package. So once you launch multiple nodes, you sometimes need to visualize, all right, what's going on, how many nodes are running, which nodes are running. And let's say if you want to run a specific node, you want to check its status, then you can just list down all the nodes using this command, ROS node list. And then to retrieve the information about that node, that specific node which you're running, you can just run ROS node info node name. I'll show you everything while we start working on Gazebo regarding this ROS node. So next important part which about ROS is ROS topics. So consider when every nodes get registered into the master, these topics are like a channel or a bus or a pipe which helps to send the data from one node to another node. So every topic is a name over which a node can publish or subscribe. So on a single topic, one node can publish and multiple nodes can subscribe. And this stream of messages is like a pipeline for sending the data. So just like ROS nodes, you can list down all the all the topics which are being published, and you can echo those topics. You can see what is getting published on that topic, who is getting subscribed to that topic. You can also get the information about that topic, like what is the message format which is being used, what is the frequency of that topic, all these things. So ROS master, then ROS publisher, and ROS node. So once you get registered on the ROS master, ROS node 1 can publish messages on ROS master, and node 2 can subscribe those messages using these ROS topics. So once we say we have the tunnel to send the data, we need to define the data structure for every type of sensor message which is getting passed. So if you're working in vision, you know that image is a xy, image is a matrix of 2D, and you need to send the data over the network. So what ROS has done is that they have gone and developed a data structure for all the topics which you can use. So let's say if you're sending point clouds over the data over the topic, so you can use a point cloud message data structure, and these these has a lot of nested structures, so of integers, floats. Then there is strings also available. Then there are arrays, matrix, everything. And if let's say if you are using your own sensors, like if you are came up with a new sensor and ROS doesn't have its own data structure to send the data of that specific sensor, you can define your own messages and in the ROS architecture, and you can use them in the system. So this is the flexibility which ROS gives you while sending your data over the topic. So over here on the topic, you can see this message. So this message has a number. It's a number which is an integer, a width which is a double, and description about that message which is a string. So one of the examples of ROS message is the pose example. So let's say you have a robot in to 3D world. That robot will have a point in the free space or a pose in the 3D world. So that could be X, Y, and Z in the 3D world. And this X, Y, Z, these are all float 64 type data type. And then there are now this message over here is not a timestamp message, and sometimes there is a requirement. Actually, to be frank, most of the times there is a requirement of timestamp messages in the robotics, because we need to keep up with the incoming data which is incoming data with the time, so you can take the decisions according to that. So for that, they have defined a pose message which is timestamp. So here we have header, which is header of this message. So this header contains timestamp, string frame ID. So what is the ID of that frame, and the sequence. Along with that, it has also the message of the pose, which is XYZ, and quaternion data, which is XYZ and W. So this is what basic ROS core basic ROS core things are there in ROS, which you need to know. So moving along, there is a ROS launch tool which is available. So what is that? Is that when you have multiple packages in the system, you need to launch those packages at a single time. And to launch these multiple package, ROS has provided us with ROS launch files. So what these does is you can list down all the nodes which you want to run, all the packages from the packages, and it can also run ROS core if it is not it has been set before. So if you have don't have ROS core running, but if you want to run a package quickly, so you can just go with ROS launch. So ROS launch, to launch any specific file or launch file which has been predefined, you can go with ROS launch and the file name of that launch file, or else you can go with the package name and the file name. If you are in that specific folder, you can go by this way, ROS launch, file name launch. But if you are in the Catkin workspace, which is where you develop all the code, you need to source the environment to that Catkin workspace, and then you can use the package name. Then uh, then we come to Gazebo. So the thing about Gazebo, like why we need to use Gazebo. So what is the requirement of the Gazebo in this whole world? The thing about Gazebo is we don't have thing about robotics is we don't have access to sensors sometimes, because sensors are costly. Then there might be a not a, won't be an availability of the sensors in the market, and you want to prototype very quickly. So during these times, Gazebo comes very handy, because what Gazebo does is it simulates all the rigid bodies, 3D rigid bodies, its dynamics and its kinematics as well, and it can simulate variety of sensors. So sensors like Kinect, Intel depth sensors, then wheel odometries, lidars, 2D lidars, 3D lidars. All these lidars sensors have been built up in Gazebo by many people of the community together, and they are combined in a single package. So you can use them to develop your own algorithm if you want to test it out, or if you want to develop a specific product, you can first simulate it and then go with the actual hardware of that product. So the good thing about Gazebo is that the people of ROS, community of the ROS, has integrated very closely with ROS framework. So whatever you're doing on Gazebo, what you're simulating on Gazebo, all that data is you can access, you can control the vehicle, you can see the data of the sensors. Everything has been integrated very closely with ROS. So to run the Gazebo, we can use this command, ROS run Gazebo, ROS Gazebo. Now, this will launch an empty world of Gazebo, not something which you can see here in image. This is one of the simulations done by ClearPath Robotics, but it will launch a empty world. You will feel that now how to use Gazebo will come into the next phase. So let's if you want to start with Gazebo, first thing we need to understand is robot models. Now robot models are something which are written in XML format, and it represents all the kinematics and dynamics of robots, which of the actual physical robot, and you can give it visual representation and how it can collide with the environment. Now these robot models are written in URDF, but they can also be written in chacros. So chacros are nothing but URDF but with the added on functionalities like including different files, including different, you can create your own parameters, you can create your own macros. So Shacros is a better version of ERDF, and we tend to usually use Sacros. So what is URDF? Like how it describes a robot, if you ask. So thing is, every robot has two major things. The first thing is link, and other thing is a joint. And using the combination of these two major elements, you can create a whole description of a form of a robot, or you can say a description of how these two elements combined together forms a robot. So here in the image, you can see in the link one, this is the base link of the robot. There is a joint over here, which connects the link 3 to the link 1 using this joint. Now, these joints can be of multiple types. It could be a pneumatic joint, it could be a rotational joint, it could be an angle, continuous rotational joint, or it could be specific angles defined to that joint. So, Gazebo has provided us with a lot of joint, and I can show you that over here. So, hold on. So here in the Gazebo, I'll share the link in the chat as well. So here in the Gazebo, you can see there are multiple different joints which you can define to come up with your own robot which you need to define properly. And using these links, using these joints, you can uh, define them in a specific format and come up with the robot. The thing about Gazebo, thing about this whole thing is that we need to keep a track of what is happening in these joints, because when we are talking about robot, we need to understand how it is moving in the environment. So if say if you have a 6 DOF arm, or an arm, you need to understand how that arm is moving in the environment to plan things, or to come up with the uh, path to reach to some goal which has been presented to it. To For this, there is a transformation system available in ROS, which usually is called as TF. So what it does, it keeps the track of all the joints with the timestamp data of that joint, and it maintains those relationship with the of the all the joints with the time. So you can go back into the simulation, or if you can go back into the data which you have collected and understand where your robot has done mistakes in making those movements or making those plannings. Then you, this has been implemented as a publisher subscriber model in the ROS. There is a TF and TF static which is available, which you are going to use in just a few minutes. So what we'll be doing today, like I have given you this lot of information about ROS, about Gazebo, about robot models. So today we will be developing a differential two-wheel differential drive rover. We will be adding a camera sensor and a Hoku lidar sensor to it, and we will visualize those sensor. We will add a differential drive controller to this robot, and we will also add a pre-built gazebo world to the simulation. And finally, if time permits, we can go for SLAM algorithm, G mapping algorithm, with all the to create a 2D map of the gazebo world. So this is what I have planned for the whole rest of the workshop. So if you have any questions, please ask them in the chat. All right. No one has questions right now. So let's start with the workshop then. So here, l- so when the most of the times you have is like you need to first start with the basic uh, workspace of your robot, which has to be maintained. So let's say here I have created a Catkin workspace to save some time. There is a good documentation of how to create the Catkin workspace, and that has been provided on the ROS website as well. So I'll drop that link as well. So this is how you create basically a Catkin workspace, and here is where you implement all your code, keep your packages which are required, and there is a specific structure to this Catkin workspace. So here, if I say ls, you can see there are three different three different folders. Out of these, source is the most important one, which we need to fiddle around or we need to work on. But devel and build, these two folders are not to be touched most of the time, because that is used by Catkin CMake, which is used to build all the code for the uh, directory. But we'll be mostly working with the source file. So right now, if we move to source file, I have created a few of the packages which we'll be using today. So these are the three important packages which we'll be working together today. So first is mobile robot description. So what robot description is that here we will describe how using URDF, how a robot will be, how will the joints will be, and uh, how it will move using a differential drive controller, and what sensors to be added to that specific robot. So if you see over here, there is another there is another workspace. Sorry, this is another package in the workspace, and this has its own structure to it. So when you're making a description about robot, you need to have some launch files. You need to have the meshes of that specific robot, which I'll tell you about later in the workshop, and the URDF. So in the URDF folder, if you move, here, there are we'll be defining our own chakro, which is just a URDF, and here in this chakro, we'll be mentioning about our robot. So here I have opened up the chakro over here, chakro file, and currently it is completely blank. There's nothing in it. The first thing about Chacro is that it is an XML file. It is nothing different but an XML file of just how we code HTML, or if you don't want to take it as a code, but yeah, if you how we write HTML pages, you use XML. Similarly, in writing robot descriptions or chacros, you can call them, you need to use you need to use chacros or XML type. So let's start with describing the robot. So basically, first we need to define that this is an XML file, and the version of this file or version which will usually used is 1.0. And now here comes the thing. When we are writing robot, the first element of this XML file is the robot, and this is the main encompassing all the sensors, all the links, all the joints of the robot. So first thing about any robot is that it has a base link to it, to which everything has been attached. So here in the image, you can see, uh, hold on, I'll zoom in a little bit. Here you can see this orange part. This orange part is the base link of the complete robot, and everything has been attached to that base link. So if we go back to this thing, the first thing which we need to do is create a base link of the system. So to create a link, we use the tags of link, and every link has a name attached to it to for the reference. So for this, we'll be calling it chassis. Now every link has its own different parameters that needs to be defined. The first one is the pose. So if you start with the pose, you need the pose is nothing but x y. What are the coordinates of that system of the link in the oh sorry what is the pose of that system or that link in the gazebo world. So here you can see I will define this pose as 000, which is xyz. I'll add, so pose has x, y, z, and rp, roll, pitch, yaw. So XYZ, we all know what is XYZ. But if you are new to robotics, or if you're just starting, then there is a concept of roll pitch yaw. So roll pitch yaw is nothing but how the system has been rotated with respect to x-axis, y-axis, and z-axis. So if that link has been rotated with respect to x-axis, we call it as roll. Then roll can be counterclockwise or clockwise. So if it's counterclockwise, it is a negative roll, and if it's a clockwise, it's a positive roll. Then the pitch is the rotation about y-axis, and same, if it's clockwise, it is positive. If it's anti-clockwise, it is negative. And yaw is the rotation of the link around, or any robot around z-axis. So yaw around z-axis. So your is also same like roll and pitch. It is positive if it is clockwise, and it is negative if it is anti-clockwise. So here I'm defining the pose as 0.1. So why 0.1, you would ask? Because uh, when you create a link, it needs to be away from certain distance from the ground, and this 0.1 is in meters. So XYZ, or the point in the gazebo world, is in meters, and the rotation is given in radians. So if you move ahead, next thing about a link which we need to mention is the inertia of that link. So this inertial, or about this link, tells us about its mass. So this parameter, or this tag, has its own subtags, which is mass first. Then this mass has a value. Now this mass is again in kgs, because ROS, or gazebo, basically uses meter, second, and radians units. So whatever the mass which we define will be in kgs. So here I will be defining it as 10 kgs. Then next thing of tag which comes under inertial is origin. So origin is where your robot is starting in the gazebo world. So this origin is in 3D space. So it has again x, y, z, and roll pitch yaw. Yeah,
Actually,
yeah,
sorry to interrupt you, Mr. Ajit. Can you
yeah,
increase the font size? Yeah.
yeah, yeah. Is it visible now, Mushi?
Yes.
Okay,
Uh, Thank you.
okay. So inertial has a mass of the of that link, has the origin of where that link is getting spawned in the gazebo. Now this origin is again XYZ and role pitch yaw. So XYZ will be 000. Sorry, Y will be 0, but Z will be 0.1, and role pitch yaw will be 000. Now, next thing which needs to be included in the inertial tag is the inertia of that link. So right now, uh, when you see inertia tag, what does it mean? So basically, every link or every link of the robot has some inertia attached to that thing. That inertia comes from the mass of that link, what are the geometric shape that has been defined to it. For the time being, I have calculated the inertias of these links, so just to save some time, and I'll be adding it as over here. But I'll share you the link of how to calculate these inertias. Hold on, I'll just add these and I'll share that link. So uh, most of you, like when you're starting with gazebo, you will be asking a question, if I have created a link, how would I calculate that link's inertia? So the gazebo has given us a quite good tutorial on this, on how to calculate the inertial matrix of a specific link which you develop. Give me a second. Uh, yeah, so this is the tutorial which has been given by the gazebo. So here you can see that link has a specific mass, it has a center of mass and a moment of inertia matrix. Now this matrix can be computed using a software called Mesh Labs. So this is also an open source available software which is used for visualizing 3D CAD models or point clouds which you generate in your system. I'll be sharing this thing in the chat so everyone can see it. So this Mesh Lab software packs many algorithms to process this 3D data. Now this 3D data can be of anything. It could be point cloud, it can be meshes. And if you have point clouds, you can convert those point clouds into meshes for computing different volumes of it, moment of inertia of it. So here you can see someone has created a point cloud and it is filling up holes using the algorithms available in that software. So in Gazebo, Gazebo has given us the tutorial that uses software to compute the moment of inertia of a specific link which you are going to use. So I'll be sharing this as well in the chat. If you in future, if you're creating your own model, instead of using some pre-available models in the ROS world or ROS community, you can use this tool for computing the inertia matrix of your links. So here I'll go back to the code again. So here I have computed the inertia matrix for the specific link which I'm going to make here. Now this link is it is a rectangle link, uh, which is a base link which can be which everything gets connected to this base link. Now next thing, when you're defining the link, now this is the end of the inertial link. You need to mention three things in this inertial link: mass, origin, and the inertia matrix of the in the inertial of the link in this inertial inertial tag. So next thing when it comes to defining a link is the collision, or what will be the geometry of the collision and what will be the name of that collision tag. So if we start if we start with the collision tag, the first we'll give it a name, uh, and this name will be chassis. underscore collision. So this will define the collision of the chassis or the base link of the system. Then, so once we create the, so what we define in this specific tag. So here we define the geometry of the collision box. So um every link has a geometry attached to it, and every link has a collision geometry to attach. Collision geometry. That geometry could be a box, it could be a cylinder, or it could be a sphere. Now these are the primitive shapes which are present in the gazebo. Now, using these primitive shapes, we develop the robot, and these primitive shapes needs to be they are defined in the gazebo code base, but you need to provide what kind of dimensions will be of these primitive shapes. So if you say if we say that geometry of this collision is a box, and this box will again have a size. Now keep in mind that this box is a cube or a cuboid. So this will be having x, y, and z again. Now here for this specific chassis, I'm going to make it as 0.4, 0.2, hold on, and zero point 0.1. Now, now we have defined. Hold on. There is a small mistake. Now, once we have defined collision, next thing comes while defining a link is how it visually looks in gazebo. So there is a tag named visual, and visual will be having its own name or to access it, if to access that specific tag. Now for this, I'm giving it as chassis visual, and again this link, again this tag will have their own subtags. Now just like we defined the inertia of this matrix, the visual will be having its origin, and to come we will, for this visual tag will be combining these two both. So this thing will be having origin of where it is starting. Now origin will be xyz, and again there would be rpy, roll pitch here. So this for this visual, I'm keeping it as 000, because it takes this 000, or this visual is where is related to this pose. So if you give it as 0.1, whatever you have defined over here, it will be termed in terms with this. So whatever visual is getting defined, it will be 0.1 in z direction. And similarly, if once you define origin, we'll be giving it a geometry. So that would be the box. So this box is again 0.4, 0.2, 0.1, similar like what we have given for the collision. And next thing is these are the main three things which needs to be defined while defining sorry, four things which needs to be defined while defining link. So just to recap everything again: pose, where the link has been situated in the world. Now since we are starting from 000 in the world, it would be placed 0.1 meters in the z direction. It would be having an inertial, it would be having a mass of 10 kgs, and the origin will be this 0.1, again 0.1, which is in the z direction, and the inertia of that specific link. Now this collision matrix will, now this collision is again which we have defined in terms of a primitive shape, which is a box over here. And for visual aspects, we can see this is 0. You can, sorry, for visual, we have again made it as a box for with x, y, z as 0.4, as 0.4, 0.2, and 0.1 respectively. So this is first we have defined as link. Now there would be the next link. Uh, Now if we go back to what I told you just before, so this is what we have created, our first link. Now to join the second, let's say if we create one another link over here. Now to these join these two links, we need to define joint as well over here. So let's create that second joint as well. Sorry, second link before joining them. So next link which I'm going to create is a caster wheel, which we'll be using for the robot. So this link, uh, yeah, so there is a question by Pratham, why we have defined the box twice. So Pratham, there are two reasons, sorry, there are two things for which we have defined box. The first one is the collision, and the second one is the visual aspect of the link. So collision will also have a box size, or basically a box shape, and the visual will be also having the box shape. So when you define link, you have to define how visually it looks. So visually it will be looking like a box. How collision will work in the world, so which that will also again work like a box, and there would be the inertia to that specific box, which we have defined over here. That inertial will be again, which will be mass, its origin, and what will the inertia matrix would be. Do you still have the question, or did you understand it? Okay. So moving on, the next link which I'm going to create is a caster wheel. Uh, okay, so there is another question: what is collision? So when you're simulating things in the world, when say you have a robot which is moving towards a object placed in in the world, so when it collides with that, let's say it is moving in a straight line, it is right in front of that robot, and it collides. Now to understand that whether that robot has collided with that specific object, we use this collision tag, or this collision geometry which we have defined. So did you get it? Do you want me to repeat it? Okay. So okay, moving on. Does anyone have any other questions before we move on to the next link? All right. So there are no questions right now. So next thing which link which I'm going to create is a caster wheel. So caster wheel, for what the robot which we are going to create is a differential drive robot which has two wheels and a caster wheel attached to it in the front, for so that it won't fall, or basically it could balance itself without presenting any kind of friction, or the uh, another kind of control which link which we have to control. Sorry. So caster wheel is a very specific link. I will show you what caster wheel looks like. So you would have seen these kind of caster wheels while making any robot. If you have done any kind of line follow robots, you must have used these caster wheels to stabilize the robot. And these caster wheels, we don't control it. It is just there just to stabilize the robot frame. And most of the controlling of the robot frame is done by the two wheels which we have in the back of the robot. So we will be creating those two wheels as well. And right now we are creating this caster wheel. So caster wheel, hold on. Yeah. So just a second. Yeah. So next thing, caster wheel. Now this will also have its own mass. Just a second. I'm facing some issues. Give me a second. Just a second, guys. Okay. So hold on. Yeah. So next thing we should be doing is developing the caster wheel for the robot, and this caster wheel will come under the link tag as well. Uh, Here we will be defining this caster wheel's collision model again. Give me a second. So let's name this link as caster wheel. Again, this caster wheel will have these four basic tags, which every link will be having in the robot which we'll be making. So let's just copy paste this thing. Hold on. Now this caster wheel be in y direction. In z direction, it would be in point 1. Now this we have to move in x axis as well. So that would be, let's say this would be 0. Yeah. Now coming to next thing, the x-axis that will be in minus 0.15 and 0, and for y y would be 0. For z it would be minus 0.05, and roll pitch yaw would be again 0, 0, 0. This would be having a negligible mass, so let's say go with 0.5 something. Then just a second. I'm facing some issues actually. That's why I'm not able to. Um, so give me a second. Yeah. So there is one more thing which I forgot to mention is that every link in the system, uh, every link in the system has a gravity tag attached to it, and we need to mention this gravity tag along with that link. But this is given differently. So this has been this is defined as, hold on, I'll show you guys. Gravity. Yeah. So when you come to simulation, you have to mention whether that link is going to face the gravity or not. So here I have mentioned that, sorry, for chassis, uh, for the chassis, it is going to have a gravity and it won't be turned off. So next thing would be, sorry, coming back to caster wheel again. Uh, yeah. Now coming back to caster wheel again. So this would be it would be bit ahead in x at axis. It would be above. Sorry, it would be above in y axis and ahead in the um x-axis. So if you can, we can visualize this again later, but right now it has just visualize that there is a rectangle, it's a cube, then that cube in just front, sorry, a keyboard, in front of that keyboard there is a caster wheel attached to it, and this is how we're defining it. Now, this caster sorry, this caster wheel will be spherical in shape. So when we go to visual, say when we go to visual, sorry, so this would become caster collision, and this will become caster visual. Okay, so when we move ahead into caster wheel, the first thing we need to define is the mass, which I have given it as a negligible mass of 0.5. Then we have to define its origin. So this origin is again with respect to this pose. So it would be 0, 0, 0, because pose is where we start with that specific, we move that specific link to that position, and from that position we need to define it further. So since it would be it would be in the center of that, or we can say it could it is on that center of that point, we need to don't need to define it ahead, or how it will move in xyz. So here we will keep it as 0, 0, 0, and for collision matrix, I have again computed thing this for this. It would be 0.01. For IYY, it would be again 0.01. And for IZZ, it will be again 0.01. You can again to compute the inertia matrix of any specific link, you can use MeshLab software. Then for when coming to collision, for collision, since the caster wheel is in type is a circular shape, so we'll be defining here geometry as sphere. So when when we define here at a sphere as a sphere, it takes in takes in radius as a parameter. So this radius will be very small. Uh, Hold on. Much have to find it. Yeah. So here I'm going to define it as 0.025 because it needs to be very small. It doesn't have anything to do. Then this next thing that coming to caster wheel is its visual model. So now we have defined the collision model, we have defined the initial model. Now we have to define the visual model. So similarly, like collision model, the visual model will be also hold on. Yeah, visual model will also be a spherical in shape. Will also be spherical in shape and with the same radius as well. So geometry, this would change to sphere, and again the radius would be 0.025. The origin, we'll keep it as it is. RPY will keep it as a Z for right now. We'll simulate it and check how it is behaving, and then we'll tweak it a bit. So we have defined a link for caster wheel. So this is the pose of it. This is the inertial matrix of it, collision matrix, collision tag of it, inertial matrix and inertial tag, then visual tag. And now to connect these two links together, the caster wheel link and the chassis link, we need to define a joint. Now this joint will be having tag name of joint. Now this joint tag will have a name. So let's give this as chassis caster joint. Now this joint, there are types of joint which I mentioned previously. So this joint will be type fixed. It won't move, and because caster wheels are fixed to the robot, it doesn't move. That joint doesn't move. So here also we'll be keeping it as fixed. And inside joint tag, we need to define what is the parent of that joint and what is the child of that joint. So going back to our PPT, so here we have defined link 1, we have defined link 2, and here is what we are defining. So here we are defining this joint. Now this link 1 is a parent link and link 2 is the child link. So this child link will attach to the parent link via joint 1. So if we go back in the code, hold on. Yeah. Yeah, if we go back into the code, here we have to mention the parent link. Now this parent link is our chassis, where everything is getting connected. Every sensor, every different links are getting connected, and our child link will be uh, caster, caster wheel link. Now remember, we have given name to the links, and these names need to be similar to which we are mentioning over here. So I'll just grab this. So now we have defined the parent link, which is chassis, which we have defined it over here. Then we have defined our caster wheel, which is a joint, a child joint, sorry, child link, which we have defined over here. And now we need to define where this joint is. So that would be the origin of that joint. Now this origin will again have XYZ and RPY. So now for this link, the origin of this joint will be 0.115 for X, for 0.0, and for Z it would be 0.07. Now I'll tell you how I came up with those numbers, but a little bit and when we start to visualize the system. But right now just take it that I have come up with these numbers. So for RPY, this will be hold on. Now for RPY, there would be no rotation in pitch and yaw axis, but there would be rotation in roll axis. So that will be minus 1.5707. Now remember, this roll, pitch, yaw are always in radians, and XYZ are always in meters. So what units which Gazebo uses is meter, second, and kg for the mass. So once we have defined this parent link, these two links, parent and child, and the origin of this joint, sorry, and this joint, we let's see what we visualize. Hold on. So I don't know why it's not showing up. Give me a second. Saved it. Yes, I saved it. No name. Oh, okay. So one thing which I have forgot to mention to everyone is that in robot, this tag, we have to give it a name. So that name, we have to give it name to this robot, which will be used by the ROS in the parameter server. So what is parameter server? You will say. So parameter servers are a bunch of parameters which can be which are loaded once we start the simulation, and using these parameters, Gazebo and ROS does the simulation. So right now I'm naming this robot as mobile robot. And one thing which we need to mention while using Chacros is we have to define the namespace. So this is the XML namespace for Chacros, and this is the link to that namespace. Now let's see whether it compiles. So you can see the cube over here, which we defined earlier, and I don't understand. Give me a second. So there is problem with the caster. Ma'am, when is the break?
The break is at 3 o'clock. 3 to 3:15 will be the tea break.
Okay, right now I'm facing some issues with my
Yeah,
computer,
sure,
so
sure.
I need to restart. So can we just
Yeah,
move that break just 10 minutes ahead?
yeah. So, we will end this session for now, and we'll take a tea break of 15 minutes, and then we can continue with the session or demonstration of the this thing.
Okay,
So I
I
would
need
like,
to just mute myself, right? I don't need to leave, right?
yeah.
Okay.
Okay. So am I audible?
Yeah.
Yeah. Okay, so we'll take a break till 3 p.m. tea break, and then we'll start with this session again. So thank you, Mr. Ajit, for this such an informative session, and you have demonstrated DROS integration with this gazebo, and you have really made researchers aware about working of ROS. So I think everyone, I'm sure everyone have benefited from this session. So with this positive note, I would like to conclude this session. So thank you, Mr. Ajit, and thank you,
Yeah.
participants.
We'll continue this session ahead in next 10
Um,
minutes.
yeah, next
I'll just
15.
reboot my system. I'm facing some issues actually.
Yeah, sure, no issues. Okay.
Okay.
Thank you. Thank you. So, participants will take a tea break for 15 minutes and will join at 3 p.m. Good afternoon once again. So we'll resume with the session. I'll hand over the session to Mr. Ajit.
Hello, can you hear me? Hello, can you hear me?
Yes, you are audible.
Okay, is my screen, is
Yeah,
everything? Yeah, okay.
yeah,
The
it's
screen
visible.
is shared, right?
Yeah.
Okay, so I fixed the issue. So what I've done is we are running behind the schedule a bit. So I have taken the code which I have written earlier and I will explain it to you as we go. So last time when we left, we were done with chassis and we were moving up to caster wheel. So here in the code, in the caster wheel code, what I have done earlier is I have combined the caster wheel with the cube itself. So here I have just mentioned the caster wheel collision model and the visual model. Since caster wheel doesn't do much and just is a collision model, we don't need to define further how it would be its mass, how it should be inertial. We can just skip that part as well. So if there is any redundant part in your system, you can just skip that. And if you just want to have a collision model of it, you can just have collision tag for it. So for caster wheel, what I have done is I have just added a caster collision model, and here there is a bit different compared to what collision model is for base link. Now the reason behind is there are two things. First, this is a sphere. Caster wheel is a sphere, so we have to give it a radius. We have to give it as origin. This part is similar. Geometry is different. Radius here it is sphere, so it is a radius. Now we have this caster will get is interacting with the ground plane of the world. Now, once these links are interacting with the ground world, there would be some kind of friction. Now here the in gazebo, if you have developed a very detailed model of your robot, you can provide the friction coefficient and how it would slip on that specific surface which you're using. So here, since this is a very basic model, I have kept the and basic model, and this is a caster wheel. I have kept the friction zero, since caster wheel doesn't provide any friction to the robot. In reality, there would be some kind of friction, but we are assuming that it would be zero and it would be completely slipping on the surface. So here under the friction, it would be under the uh, tag of ODE. So next thing about caster wheel is its visual aspect. Now for visual aspect, again, it would be a spherical geometry with the origin, which I have provided over here, and a rotation pitch and yaw. Now this we don't need to join it again, since I have combined it with the base link itself. So next we move on to left wheel. Now just to understand what model is going to look like, here it would be looking like this. Hold on, so let me add the robot model. So this is what we call RVs. Now this is a tool provided by Ross for visualizing different aspect. So right now there is an error. I will tell you why that error is in the future. But you can see the caster wheel over here. So what right now happened is that we have created this robot. Now, since I have copied the code which I have done earlier, it has also included the wheels. But here you can see there is a caster wheel. Now what we'll do is we'll add colors to this block. And to add colors, we have to just provide under gazebo tag, we have to provide a material color. So hold on. Here before starting anything, you can if you have developed some HTML code, you will understand what is like to develop what is right to write the code. So I'll just copy it and I'll give you an example of it, how it works. So okay, so here I have defined the material and its color. So if you have a material named black, you can assign a color to it. So right now here I'm assigned a color as black. So this is how we defined colors using different. It's a 4-bit. It's a 4-bit. So using that combination, you can provide that color to it. Then I have provided different colors as well. So like there would be a blue, there would be a green material, gray, and specifically I have given orange and brown, red, and I have used these most of the system. So now when I compile it again, you can see the color as well. So I'll again add the robot model. Now, bear in mind this material color, you won't be able to see it over here. But when you run the gazebo version of it, you will be able to see that color. So here you can see the color which I'm talking about. So I have given the orange color to the base link, and here is the white color to the caster wheel. Now going back to the code again, this is what color is. Now here is the caster wheel, here is the chassis which we have done, and now we will move on to the left wheel. Now how left wheel is developed. Now again, just like basic base link, caster wheel, sorry, the left wheel also have its own three main tags of collision, visual, and inertial. So under collision, uh, here this geometry of this thing would be cylinder. So now there are three types of geometry which we have come across. One is sphere, the second one is cylinder, and third one is a box. Now these are the three basic type of geometries provided in the gazebo while developing any kind of link. And using the combination of these different geometries, you have to come up with your robot model. So in left wheel, it would be if you if you take a wheel and if you rotate it, you will understand that it's a cylinder, right? So for geometry, I have given it that a cylinder with a radius of zero point 0.1. Now this zero point 0.1 radius is in meters, so it comes to around 100 centimeters, and length is about 0.05, which is the thickness of that wheel. Now this will have its origin at 0, 0, 0, and now here I have rotated it bit. So I have rotated in the pitch axis and in the yaw axis. Now you can see over here the robot model, and if I do the changes over here, if I just make it 0, 0, you will understand how the wheel is spawned in the gazebo world. So I'll just stop the simulation again. I'll do start it again. Now, when I made that pitch 0 and 0 again, you can see the robot is collapsing because it is not getting spawned correctly. And if we go to RVIS, we can visualize it much more clear. Give me a second. Boss, let's see, did I save that? Yeah. Okay, I have changed collision model. Let's change the visual model so you will understand what is happening. Okay, now, all right, what happened? And it changed. Sorry, I changed in inertial. Here it is the thing where I have to change. Sorry, guys. Just see this profile. Just close watching. Yeah. So now you can see why the uh, if you if I just start the collision, you can see the collision hasn't been shifted since we gave the rotation to that collision model. But here you can see the visual model is shifted by in pitch and yaw axis. So if we change it in pitch axis, hold on, I'll do changes one by one so you'll understand what is happening. So right now I have just changed in pitch. I have kept the yaw still 0, and you will see the wheel is turning again, or wheel is rotated in pitch axis. Now pitch axis is rotation along y axis. So yeah, see now the pitch wheel has been shifted or rotated, you can say, in y-axis. Now I'll again rotate in yaw axis, which is z, which is around z. So if we go back to the code again and I do here 1.577, 1.5707. Now this number is pi by 2, which is 90 degrees. Now remember again, your rotation is in radians. So when we divide it by 2, this becomes 90 degree. So CO here. Now this, I will add the axis as well so you can visualize what is happening. So here red bar or red, this thing is x-axis, y bar is green axis, and z bar is z-axis. So here you can see that this wheel has been shifted from its origin by a meter. So here is the joint of that specific wheel, and it has been shifted by +1 over here. So when we are defining any link, we don't need to mention the origin of that link into the link tag, but we need to define the origin of that link in the joint tag of that specific link. So here you can see it is 0.1, 0.0150000. This is the actual origin of that link. And here, from whatever the changes which you are going to do in link tag will be reflected. So let's get this back to 0 and see what will happen again. So now that wheel is back to its origin, since we haven't provided any uh, changes or any translation or any rotation to that wheel in that specific link. So remember, when defining any origin of any link, that is defined in the joint itself. So going back to the joint, next thing that needs to be defined in the joint is the child and parent, which we were discussing earlier. So here, the parent of this link of this joint is chassis, and the child link is the left wheel. So you can go, if you go back to the robot model again, this this red block over here, this red block or red box, you can say, that is the main parent child parent link of all the robot. Here you can see chassis is the first one, then comes the left wheel and the right wheel, which are the child of these parent link. Now if you go back to code again, I have defined axis. So what is this axis and limit effort over here? So this axis is how this joint is going to rotate. Hold on. Okay, so this is axis tells us how that joint is going to get rotated, and what in what direction. So if we when we rotate that cylinder from resting position, which was spawning position, when we rotate it by minus or plus 90, then we rotate it in y-axis. So why, I'll tell you. So this right now is a rotated wheel, and when and before we started, let's say, let's go back to visual. Let's just makes it 0 and 0. You'll figure understand. Yeah, this is the spawning position of that specific wheel. So once we rotate it in pitch, that is like this, basically like this in this direction, and then we rotate in this direction like this, which is in from pitch and then yaw. Once you rotate in that, the axis of rotation that wheels become in y-axis to for making that robot move ahead. So if we go back in the code and we change it back again, and instead of y, I cannot show you rotation without any control. So right now just understand ki uh, rotation is in y-axis of that specific wheel. And if we go back into the wheel axis, sorry, wheel transform, I go back. Yeah, so this is how axis looks like for that wheel. And right now, I just hold on, I'll just compile it again. So it'll be confusing. Yeah, so this is again rotated wheel, and we go back to left wheel, and we start it and when show its axis, you can see uh, you can see the y-axis coming out of here. Remember the x red one was x, which is in this direction. Sorry, which is in this direction. You can see it protruding a bit over here. This small thing. Uh, Yeah, this small thing. This is X, this is Y, and this is Z. So the rotation will be along Y axis for this wheel. And similarly, for the right wheel, if we go into right wheel and turn on its axis, you can see again the rotation of this wheel is also in Y axis. So when we go back into code and see the definition of right wheel, you can see it is very similar. Right wheel joint, you can see it is very similar to what we have written for left. The only thing that changes is that this joint moves in the negative y-axis. So why is that? So here is the center of our spawning location. So when we move x direction, positive x direction over here, then for right, sorry, I'll just show you side by side. So yeah, this, yeah. So for this is the left wheel. Uh, this is the left wheel. This is the right wheel. So the right wheel has been moved into negative x direction, and the right wheel has been moved into positive. Left wheel has been moved into positive left direction. So why is it? So here is the origin, and this right wheel is to the right side of the origin, and uh, this is how axes are aligned. So here is the right wheel that has been shifted to the I'll just show from this point, that has been shifted to the right in so how it is moved, it is moved point 1 in x axis. So this is how it is moved. Then it is moved minus 0.15 in y axis. So that is how it is moved in this axis. So similarly for the left wheel, that has been moved zero point 0.1 in the x axis and plus 0.15 in the x axis. Sorry, y plus 0.15 in the positive axis. So both the wheels are similar. Both will have the same kind of description, same kind of collision, visual and inertial. The only thing will change it is their origin and their link name. So here you can see again the joint for the right wheel also is the same. The origin is this, which we discussed just right now, and there is a child and parent link. So the child link is the right wheel, parent link is the chassis, with this axis of rotation and limits and joint properties. Now, joint properties is something which I haven't discussed yet. So if you have some kind of specific robots which have very specific joints to it, and there is some kind of dampening and there is some kind of friction to that joint, you can also provide those kind of info over here. But right now, since we are doing a very basic simulation, I have just given damping to be 0 and friction to be 0. So if you have a joint where you have attached some kind of spring for shock absorption, there you can provide some kind of dampening to the joint. So right now, since the model is very basic, I haven't provided it anything. So this is how wheels are defined, or basically child links are defined, and how child links are attached or joined to the parent link. Now, next thing comes is sensors. Now, Gazebo, along with the robot model, also provides sensor models, and Gazebo is very computationally intensive thing. So what they have done is they have shifted the world computation, robot computation, and the world computation to CPU, and they have shifted the sensor computation, sensor related data computations to GPU. So if you have a GPU in your system, that might help you a little bit in doing the simulations as well. So first thing, we are going to talk about cameras. So here is the camera. Just a second. Give me a second. So now we are going to talk about camera. So sometimes there is sometimes if you don't need to show the actual camera on the robot, you can completely avoid it and you can just go along with it and just add the sensor to the robot. But if you want to add a specific a specific model to that specific sensor, you can also add that as well. So right now I haven't added any camera model per se. So if you go back into the code here, you can see I have added camera over here. So this is the camera uh, library which is provided by the Gazebo. So how to add a camera or to the to your robot is here you have to define first so what I have done is I have defined a camera properties. So this sensor type, so when you're defining any sensor, this is how you do it. So you start with gazebo tag, you give it as a reference name, you provide it a material, and you define that is a sensor. So for that, you have to use the sensor tag that spans till last over here. So under sensor tag, you have update rate, which is the hertz of how the data, how many hertz the data is getting published. Just give me a second. I can. Sensor is, sorry, yeah. So how much hertz the data is getting published. So now this camera has name, so which we called as head, and that camera has an horizontal field of view of this 1.396. Now again, this is in radians, and the image which is incoming from that camera is 800 by 800, and the format is RGB 8-bit. Again, the clip, this is very specific to camera, how to clip the incoming image data and near and far. So basically how far it can see and how near it can see. That's how we clip the sensor range. And this is the plugin provided by the Gazebo ROS. So we once we define the camera, we need to define the plugin as well for that camera. So we define the plugin by name as camera controller, and the file name for the specific or the library for the camera is libgazebo ROS camera. And these are few parameters which are attached to it, or basically attached to this. You can say uh, camera plugin. Right now, these are available, quite freely available on internet, on Gazebo as well. If you go into Gazebo's website, you can see there is. Give me a second. If you go into tutorials, you can see there are sensors over here. Here. So here there are multiple sensors available in the system. So there are beginner here. You can use Velodyne lidars, you can use cameras, you can use Kinect. They have libraries for Kinect lidars, Hokuyu lidars, then cameras, everything. If you want to create a specific library for your specific sensor, you can also do that, and there are tutorials for that as well here. So here they have given the beginners tutorial, they have given the intermediate tutorials for how to create those lidars, how to integrate noise into your sensor, and how to develop a plugin for that sensor, and finally connecting it to the ROS. So going back to the code again, you can see now these are the parameters which were developed by the community, and right now it is these parameters. Right now you don't need to think about this. These are very simple thing. So I'll just do mobile robot camera image raw. So this is what the camera name is, what the topic it is going to publish, and what is the info about that camera. And these are the few specific things which you need to think about, or basically configure when you're developing it for yourself. Then I have added Hokuyu LiDAR to the system as well. And here also it has a sensor tag, and under the sensor tag it has, there are few different things for this, because this sensor is different to is different from camera. So you have to properly think about this one while integrating. There are scripts available on the Gazebo website as well to integrate it. So now that I have integrated these two things, I'll just give me a second. I'll, let me check if things are getting published. Uh, Give me a minute. So now what I'll do is here in a box type with given specific mass and origin. Now here there is a little bit different. You can see the thing about chakras is you can create different constants in your system. So what I have done over here is that for this I have developed I have given out a constant named chakra property with camera name as camera size and the value of 0.05. So you can streamline your development if you have written out the properties first, or you can say you have declared those constants earlier. So then you don't have to put in numbers like this. You can just directly go and you can just add that as a variable over there. So it will substitute that specific value. So for camera size, I have given it as 0.05, and for camera mass, I have given it as 0.1. So here you can see camera size box, which is a this thing becomes as cube since 0. It is for 0.1, 0.1, 0.1 size of it XYZ. Now this has the material of green and inertia, which we discussed earlier, of camera mass and the specifics of inertial tang. And then I have created a hook joint as well. So here I have created a hook link similar to what camera link is there, and I have mentioned collision, visual, and inertial again. And I'll show you another version of the code as well, uh, where we give me a second. Let me just compile this one and see if it's properly working with the camera and OQ LiDAR. Okay. So undeclared green. Plus 230.23. So I'll just complete my code in a second and I'll show the final version, how it looks. What happened again? Okay, so why is this colors are not getting. Okay, for some reason I have, so what I've done is actually for this tutorial, I had broken my code into various small sections and I have completed it, or basically I've added the sections which I removed earlier. So what I have done, I will explain it to you in a second. So here, I have added a camera link, its camera mask and its camera joint. So basically it's similar thing to what base link over here is, or basically the main link over, which is our chassis. Similarly, I have added a camera link. Oh, here you can see a small cube over here, a small cube over here, and this cube indicates the camera. Now what I have done is I have created a link, I have attached it to the body, and I have attached the sensor to the this specific block or a specific link over here. So if we go back into the code, you can see this is the link name camera. And if we go back down over here, hold on. Give me a minute. So I actually missed out a part, I guess. So that's why it was not showing any colors. Okay. The reason that color were not getting published earlier is that I missed out a part while integrating the complete code together. And here it is now, final code. Let me see if the topics are also getting published. Yes. So now, okay, I'll explain it again, what I have done. So here, finally, what I have done is before we discuss wheels, we discuss our basic link, base link. We have discussed both the wheels, and we have discussed the caster wheel, which was over here, this one. And now what I have done is that I have created two new links in the robot. One is this Hokuyu LiDAR sensor, and the other one is the camera link sensor. You can see that box, green box over here. Now this green box is another link, which is camera. And what in Gazebo you can do is you can okay, so there are no questions, right? Okay, so you can attach the specific sensors to a specific link in the Gazebo. If you go back over here, yeah, so here is I have created a link named camera, and if we go down in the camera Gazebo tag, which we talked about earlier, while adding a sensor to the Gazebo, you have to mention the reference name of that sensor. So here, if we go back to here, that specific reference name of that link is camera. And if we go down, I have mentioned the reference to be as camera and sensor type. And because here, uh, now using this tag and this library, libgazebo ROS camera. Now, this library comes along with your ROS installation, so you don't need to have any another specific installation to it. So you can see using this libgazebo and this gazebo sensor plugin, there are topics regarding camera which is getting published over here. So now these are the camera topics which are getting published. So image raw compressed, and these are different specific sense topics which are coming out from that sensor library. Now to visualize any one of this thing of this cam image data, there is a package called image view, and you have to provide the topic name to it. And here you can see the stream which is coming from that camera itself. So if we go back into the simulation, give me a second. And if we look where the robot is facing right now, and if we look into the camera feed, you can see this specific table, or you can say specific cupboard over here. And there is small mistake, I guess, in my code, because of which it is continuously rotating. But this is how you develop a basic robot model while integrating the sensors. Now, one other thing I have included, or which another sensor which I have included, is this Hokuyu LiDAR sensor, which is a 2D laser scanner, and it gives you distance. Basically, it's a ultrasonic sensor. You can think of it as an ultrasonic sensors, but there are multiple ultrasonic sensors in together, linked together, to give you at least to give you 180 degrees of data distance depth of that field. So if we go into RVIS, so here you can see the robot model, and I'll add laser scanner, and here it is getting published under the topic of MyBot laser scanner. So you can see the laser scans. You can see these little red dots. All right. So since they are very small, I'll just increase the size of them. Now you can see the laser scan. Now this is a 2D laser scanner. It will give you depth data in 2-dimensional, not in 3D. For 3D, you need to integrate Velodyne LiDAR, and Gazebo also has a plugin, a sensor plugin for that as well. Now, if we go back into the now, if you want to see the camera feed in RVs as well, you can just add it over here using the topic image, and under the image you have to select which topic you want. So there are two topics, one which is image raw and another image view output, but you will choose the image raw, and you can see this image coming from the camera as well. So here you can see this, you can say block or something, cement block. You can see there is another thing over here. There is another shelf over here. And if we go back into gazebo, you can see this shelf, this shelf, this cement block, and this circular thing. Now, if you go back into RViz, you can see this specific thing over here, and this is the 2D data for it. So till now, what we have done is how we develop a robot model, the links, the joints to that robot model, how we integrate sensor to it, and how to visualize the data coming from that specific sensors. So till now, does anyone have any questions? Because I've gone very fast because of the time limit. I thought I would miss out on the things. Does anyone have questions?
Just wanted to ask you in which particular applications this ROS can be implemented, like which in any specific applications that ROS can be implemented.
Uh, there are, you can use, and you can, there is no specific application where you can use. It is very generalized. So let's say if you don't want this world, or basically this is very specific basics world which I have created, and you want to have a different model in this thing, you can create your own models over here using by just putting selecting a model over here and then putting it into this world, and you can create a world like this. So let's say you have an arm robot and you want to make a coffee using that arm robot, so you will have a world of cafe around it, so you can create
Okay.
that cafe world as well. So if you don't want to create over here in gazebo and you have created it somewhere else, you can import it into gazebo as well.
Okay. Thank you.
Yeah. uh So this is what I had planned till now. Now, one thing which I was thinking about was implementing SLAM algorithm. Let's see if we are able to implement it. Okay. Thing is, I haven't. Uh, there is some issue which I'm facing over here where it is not recognizing my package. So what I'll do is I'll show you a turtlebot. You must have remember the in morning when Linton Joseph were giving talk. He mentioned about turtlebot. So turtlebot is one of the educational robot which has been created just to study different algorithms or to develop a specific algorithm if you want to. So if you go here, let me just start it. Now, thing is, when you download ROS, Turtlebot is already installed along with it. So if we go, I'll show you one more thing. Yeah. So let's bring up the Turtlebot. Uh, Okay, for some reason I removed TurtleBot. I guess I must have working on it and I must have removed it. So I'll just add it again and I'll show you what SLAM algorithms looks like. So TurtleBot 3. So the good thing about ROS community is that when you develop any kind of thing or any kind of open source thing, they make a lot of tutorials around it. And since TurtleBot is a educational robot, there are so many good tutorials developed on it by the community that you can just go and read about them all day long. I'll just copy paste this thing for everyone to uh, go and visit this page. So this is completely about TurtleBot 3. So now what I'll do is I'll just go through this tutorial which they have provided, and I'll create, I will do SLAM, 2D SLAM for mapping out the area which we were using it. And while mapping, I'll control the robot using keyboard teleop twist teleop keyboard package. So what's twist teleop keyboard, you will ask? So that is used the that package uses keyboard keys for controlling the robot in the gazebo world. So if we go into the tutorial over here, you must see they have mentioned out all the things very properly over here. And let's see if the thing has been downloaded. Okay, so we'll just start raw score. Okay, so raw score is already running, so that won't be a problem. And they have mentioned pretty nicely over here how to go step by step when you are launching anything. So if you go, okay, so this is they have for, give me a second. Okay, so the one link which I shared earlier, was something for actual hardware. If you have that actual hardware with you, but if you want to do it in Gazebo, we have to use a different package or different launch files which they have provided as well. So here you will see the one of the robot models which they have developed. We will see just a second. And this robot model is called as Burger for this one. So there are a few different turtlebot names, and this is what we call that. This is that name of that specific model. And before starting anything, we have to mention this parameter name as burger. So this parameter name is just selecting which version of turtlebot you're simulating. Then uh, then we need to launch the world. Give me a second. Okay, so they have provided it differently, not with the ROS distribution. So if you have a different package which they have provided differently, you can just git clone it. Now think about adding packages which are different and not provided in the ROS package system. if you want to add that specific package, you have to go into the source of the catkin library, and over there you have to clone that specific package. So once I clone this, what next step is to do is we need to compile the code or compile that specific ROS code. And to compile that thing, there is catkin underscore make. So what this will do is it will take all the packages available in the source folder, it will compile them, it will link them, and it will create an object file for the uh, nodes which were present in that specific package. So once this is done, can just what is happening? Okay, give me a second. Okay, so let me see if this package is available. Yeah. I don't understand why it is not able to pick up my package. Okay, so what I've done right now is I have installed the Turtlebot 3 package. So what they have done is that they have provided separately on the GitHub, and I just cloned it. I have cloned it into my source directory under Catkin. So if you go into Catkin workspace under source, you can see the Turtlebot simulation, and this is what we required for this basically SLAM tutorial. And if you go back over here, you can see that they have started a gazebo world, just like what we did prior. They have created a model of turtlebot 3. Now this model is called as burger. Burger because of that 3 layers, and it is also a two-wheel differential drive with a lidar over it. So this is 2D lidar. And if we see the ROS topics which are getting published, you can see these are the different topics which are getting published because of this specific robot simulation. So there is IMU, there is joint states. Now joint state is nothing but the TF transformation of the specific joints, then odometry, then laser scan. Over here you can see that. Oh, hold on. Yeah, so this is image raw, odometry, scan, laser scan, which I was talking about, and transform. This joint state is also related to joints. This joint TF takes this joint state and converts into the transform for complete system. Then there is image raw, and you can see the model which has been developed. So let's see if we were able to drive this system. Give me a second. Yeah. Now you can see there is another model as well. This is the other model is called as waffle, and Turtlebot 3 waffle. And to teleop the system, they have provided the teleop package as well. They have modified it for themselves. If you go back over here and just start that. Okay. Remember when you're starting the new node related to that same package, you have to again export the package, sorry, the Turtlebot name for that. So now it will start the control. So you can see you can move around the gazebo world using those controls. I'll just yeah. So now you can see the bot is moving. I'm using W for WASD and X for moving. So I'll just turn around. Uh, then I'll go ahead. So now this is 4 stop. So they have provided specifications of how to use that teleop over here, and there is you can increase and decrease the speed of the system as well using W. So if you start hitting W, you can see the linear velocity is getting increased and increased over the time. So it has become 0.06 now. If we decrease it, it becomes 0. Now if you go want to move the robot towards back, you can hit X and it makes the linear velocity negative. Then again I'll make it 0. And if you want to rotate the bot, you have A and D, which will change the angular velocity of the system. And just change. Okay, now this is stop. Now what we'll do is we will I'll show you the SLAM algorithm and how you create a map and save it on the system. So for doing that, they have also provided over here SLAM simulations. So again, first we have to use the Turtlebot model which we are using. So that again, since this is a different terminal, we have to again explicitly say that this is our Turtlebot model. Then let's start this again. Now then I'll bring on the SLAM algorithms. Now this G mapping is an implementation. This SLAM algorithm, G mapping algorithm is an implementation of open source algorithm, OpenSLAM, which is developed by Kyle Stachnis and his team. So Professor Kyle Stachnis is from University of Bonn, and you can see the SLAM algorithm starting over here. So if we back now, let's see. This is the. Give me a second. One frame. Why? Okay, so the reason what it was not starting is that one of the package, G mapping package, was not available in my system. So I just quickly downloaded it again, and I'll start this node package again. So now you can see the map getting generated. So this is the 2D LiDAR data. This green points you can see. This is the 2D LiDAR data, and this white boxes is where you can move the robot, and this black boxes is where you will hit the bot, or basically you cannot is the area where you cannot move the robot into that specific area. So if let's say if we just move around this specific world, it will start mapping the area. So let's just move around the map, and you can visualize the map which is coming in. So right now you can see the bot is moving in the world. And simultaneously, I'll just stop the robot over here, and simultaneously you can see the map getting generated over here. So what I'll do is I'll just go around the complete terrain, complete map over here, and I'll just map out quickly. So I have almost gone around the complete terrain. And I'll just stop over here. Now, if I go back into the RViz for visualization, this is the map of the complete area. And if you go back into the arena, you can see this is the over top view of this arena. And if you go back into the map, this is the complete map which is getting generated. Now, once you have generated this map, next part comes is you have to save this map somewhere, right? And for that, the ROS has provided map server for saving that specific map. If you go back into the tutorials again, you can see they have used the map server package. And if you run that map server, it will grab that map and it will save into your library in your directory by and it will generate two specific files, one which is PGM file and another one which is a YAML file. So YAML always links to the PGM. So if you moved around your map somewhere into the system, you have to move these two files together. So I'll just stop the SLAM algorithm and let's see what the map has been developed. If we go back into Catkin workspace where I have saved it, hold on, where I have saved it, Catkin. Yeah, so I have saved it in my home directory, and this is what the map looks like. Now this file is called as PGM files, and the other one is called YAML file. So if you see the YAML file, you can see the specifications of the map. What is the threshold which was used? What is the free? What is the resolution which was used for while mapping? And finally, the name image of that map. Now, this is 2D mapping. There is also 3D mapping, which is called, which is done by many different libraries. There are many different ways of doing 3D mapping. Most famous of them is 3D occupancy grid maps, which is also made by a German university. And this 3D occupancy grid maps package is called as Octomap. This is also available on SLAM. Sorry, this is also available on ROS. And if you want to use if you have any applications which revolve around creating a map of an environment, you can use this along with your this uh, 2D maps to create a map of the complete environment. Now, next thing about this Turtlebot is navigations. So let's say you have created this map and you want to use this map into the next thing. So that is where thing of navigation stack comes around. So what ROS community have done is that they have developed a navigation stack which will use the previously generated map, and it will localize itself into that map using advanced Monte Carlo localization method. Give me a second. Using advanced Monte Carlo localization method, and it will go from point A to point B using path planning. So here, uh, again, what I'll do is I'll go back into my terminal, and I'll just keep everything. I'll just turn off my teleop twist keyboard for controlling the robot. And what I'll do is I'll first uh, take in the map which was previously generated. So here is the navigation. So this navigation stack is what I was talking about. This Turtlebot navigation is the package, and it takes a parameter of where is your image. So sorry, where is your map? So here you can see it takes in YAML file, and if we go back into the terminal, if we use this. Okay, so now you can see it has taken the previously generated map, and it is using particle filters, which is basically localization, advanced Monte Carlo localization, and it has created some kind of hypothesis that it is around here. But if we go back into the gazebo simulation, you can see the robot is somewhere around here. It is not somewhere around here. The reason behind this is that it once it starts to move, it will get more data, and using that data it will localize again. So what we have to do here is we have to just move around in the system, and to do that we can use 2D nav goal over here. So what this is that we will just place an marker on the map with the direction, and once we place that and we go back into the gazebo simulation, give me a second, don't know why this is. Yeah, so you can see it is starting to localize. If we go back into the gazebo simulation, add one more. Let's see foods. Yeah. I guess I don't have one more library. Give me a second. Okay, for some reason I'm facing some issues, but let's see. Localization. And this is the new this scan, this highlighted green highlighted points are the new scan incoming to the robot. And you can see there are small arrows, and these arrows are the basically prediction of where the robot is. So if we move the robot around somewhere, it will start to take in data. And once it starts to take in data, uh, okay, just let me just reset the thing. Okay, so you can see now again that it has taken up the map which was priorly mapped. This is the new incoming sensor data. And let's see if moves. You can see now it has a little bit of good understanding where it is. The green arrows which were spread out earlier, now they are saturated to few other places. So what we need to do is we need to move around the map a little bit more just to get just for this robot to get more data. Let's see what is happening. Now you can see the cloud is getting the green arrow cloud is getting closer and closer together, and it is trying to localize. It is still relying on data. Now you can see one second. Yeah, now it has a better hypothesis compared to last few seconds. And if we just stop it over here, let's see. Yeah, still there is some kind of drift in the localization. You can see it still has some hypothesis that it is over here. It is over here. Like majority of particles are over here. But if you go back into the map or simulation, you can see it is over here. So there is a little bit of drift into the system still. Let's move around a little bit. Let's see what is happening. So right now it still feels that it is over here because of the data. And let's see. Oh, stop.
बोलने पहले थी
the robot with that pillar.
પહેલેથી બોલ્યો કેમ નહીં તું ક્યારનું તને કહેશે કહેશે તો બોલ બોલ બોલ
બોલતો કેમ નહોતો
ક્યારનો બોલતો બોલે
રાખીને પાછો હું આમ જોઉં છું ખીજાઉં છું તો પાછો ભાગી
Now
જાય તો પણ
you can see the map has shifted a little bit towards left more.
મજાક કરતો તો એવું કેમ ન બોલ્યો
તું બોલે ને તરત
તો બોલ્યો કેમ નહીં
કેમ તરત બોલ્યો નહીં મારે અચાનક એ કર્યું એટલે મજાક કરવામાંથી હસવામાંથી ખસવું થઈ ગયું
It's still having some problems, but let's see if we are able to give it a cool. Okay, so what I did right now is I have provided a goal for the robot to reach some place, and using the mapping and path planning algorithms, it will try to reach that goal, and it will try to orient into the direction which I have provided. So right now the robot is trying to localize. It's checking whether it is on the correct point which it has to reach. Now you can see it is trying to reach that specific point. If you go back into the gazebo simulation, now you can see the particles are very closely packed together, or the cloud of the particles are very close to each other. Now here it has reached to the position which have or the point where we have said it to go and orient itself. And if we go back into the gazebo, you'll see it has gone to some point, but there is some kind of localization error in the system still. Okay, so this is what I wanted to showcase. Basic navigation stack, how using some turtlebot or any other education robot. Then how to create your own robot using URDF and Chakros, how to integrate sensor into it, and finally how you can integrate all the things together to do mapping, to localize the robot into the unknown area, or to give a robot point it to some kind of marker or some kind of point where it has to reach. So using navigation stack, it will localize that into that map. It will go into that specific point using path planning algorithms. Ma'am, so anyone has any other questions?
હવે મારે છેલ્લે બોલવું પડશે.
Any participants have questions? Okay. What is ROS API?
Sorry, come again.
ROS API.
So ROS API, you can say there are multiple APIs. So API would be related to some kind of specific language or some kind of specific, you can say, package, you can say. So there are multiple APIs as well,
Okay.
which APIs would, you would say, like pre-built libraries, just you how to use them properly.
Okay. So, if there are no other questions, then I would like to say vote of thanks. So, on behalf of Department of Electronics Engineering, RIT, I would like to thank Mr. Ajit Mutalik for such an informative session. So, it is very well demonstrated ROS integration with standalone gazebo, as well as it has given the overview of how to add sensors and simulate the robot using ROS and gazebo. Also, overview was given for SLAM algorithm using Turtlebot. You have really made researchers aware about working with ROS environment. So I am sure everyone have benefited from this session. So with this positive note, I would like to conclude the session. Thank you, Mr. Ajay.
Uh,
And
I just wanted
yeah,
to ask everyone, like this was my first time conducting any workshop.
yeah,
So this is my first thing. So
yes.
did everyone liked it or some kind of changes that I should make into presentation while doing presentation?
From audience or
Yeah,
others, I would say.
from audience. Okay.
Actually, the with the demonstration, everyone like I was also not aware of what is how to work with ROS. Yeah, someone has written. It was nice. No changes required, sir. Yeah, it
Thank you.
was really very nicely demonstrated, giving like the person who will not know actually how to work with ROS or this gazebo simulator. So everything was very excellent or excellently demonstrated. So and presentation was also good. Thank you,
Okay.